Now let's see how we can apply mergesort. We'll first do some performance analysis to compare it to the existing Python sort implementation, see which one's better. And then we'll apply mergesort to another problem, namely how do you sort data that's actually stored on disk and not readily available in memory. To demonstrate the performance, I'm going to use this sample code here, which you've seen me use before. I'm going to create a random array containing numbers from 1 up until n. I'm going to do it 10 times and pick the average of those 10 times, because when you sort, invariably the diversity of the numbers greatly affects the performance of the overall behavior. For each of these, I'm going to do a sort using the built-in Python sort capability, and then call the mergesort that we've now implemented. So when I run this, you will see that the performance keeps pace. The first number is the built-in sort, and the second one is the mergesort. The built-in sort is at least 10 times faster than the mergesort that we just implemented. A lot of that has to do with the fact that Python is an interpreted language, and they've implemented sort using a highly optimized C implementation of a sorting algorithm they call timsort, which is really interesting. And we will never be able to outperform it. But at least you can see that the performance between problem size instances is more or less the same. The curve, I would say, the growth rate is the same. And fundamentally, that's the real issue. When it comes to sorting, it turns out that there is no algorithm that can sort better than order n log n. And there are proofs in computer science that I could roll out to show you that. For now, I'll just let you take me at my word. The type of algorithm that you use can lead to varying performance traits. And so you can have highly optimized code that performs exceptionally well under some circumstances. But no matter what you do, it will never be enough to break through the order n log n barrier. So at least I'm pleased to see that mergesort holds its own with the built-in sorting algorithm here, but naturally you should use the built-in sort for all your main functionality. But that leads me to this extension to the problem. What if the data that you're sorting is actually on disk? What do you do then? Well, if you imagine that file on disk, it is a contiguous block of memory. It's just not what you have in RAM, it's just on your secondary storage. And if I think about mergesort, it's actually something that I can apply directly to that same problem, where instead of accessing memory items, element index I, for example, I can access a particular location on disk, 1,000 bytes in, 200,000 bytes in. And you can take the exact same structure of the mergesort algorithm and apply it here as well. So instead of showing this to you line by line, I've got the full implementation here, and I'll demonstrate it, and then we'll see how it works. We first start with the idea that I need to be able to randomly generate data. I could generate random arrays in memory easily enough. I need to find some way to generate random data on disk. So I have a function that does that. Let me just scroll to the end to find it. And I think it's called create random. That will just go through and create as many data items as I want and create a file on disk that contains those. So let's just create, we'll just keep it small for now, 32. Small set. And there'll be numbers up to 1,000, so that's nice. To actually validate that I've done this, I've got another function called out, which is at the beginning, output, sorry, that would just go through and output those numbers. So there you see I've got a random collection of 32 numbers in the range 1 to 1,000. I want to sort those. Well, Python has very useful code that lets you take up data from disk, load it up into memory, and then do the sort there, and then presumably you would dump it down to a file. But I want to actually sort it on disk directly. I want to be able to do what's called external sorting. And what's really interesting is I can use the exact same mergesort algorithm to do that, as I'll demonstrate. The first thing that I have to explain, and I'm only going to touch upon it lightly, is this notion that when you're loading up information from disk, it's a very costly operation. Orders of magnitude much more costly than accessing internal RAM, for example. There's a capability that operating systems provide called memory map, which allows you to map large subsequent partitions of disk into memory for rapid access. And the operating system handles all of this for you. This is truly the best way to move data back and forth between memory and disk. And surprisingly, most programmers don't know about it because it's really an operating system's concern. So I thought this would be useful to see if you find yourself processing gigabytes worth of data that's stored on disk. This is the way that you would do it. I'm going to start my mergesort file. And as you remember, to do mergesort, I need to have an exact copy of the original data to even begin the process. So the first thing that my mergesort does is create a full copy of the disk file. This is just the nature of it. This is the order n extra storage that will allow you to perform the computation in n log n time. And I think most of us would be willing to make that trade-off. In computer science, we call it the time-space trade-off. To get better performance code, you sometimes need to store additional stuff. This is the fundamental principle in databases and indexes, for example. To get the fast performance that a database gives you, it creates extremely large index files that make that possible. But here, I only have one extra copy of the data. So this uses the shell utility module to make a full copy of that source file on disk. And then I'm going to open up access to the disk files using mmap. So one is called the destination, one's called the source. And they play the same role that they did that you've seen in mergesort. I want to sort the data in whichever those map files are between range of 0 up to, but not including the length of the file. And if I look at the code for mergesort now with mmap, it's a little longer, but I can still make it fit on one page. I'm now dealing with integers that are a full 64 bits. So now my index values are no longer 0, 1, and 2. They're 0, 4, 8, and so on, because I'm going to use a full 4 words to store each integer value. So what mergesort map does, it has as its base case 2 steps. Either the range on disk file, the locations into the disk file, are within 8 bytes of each other, which means that it's just one element, so I don't have to do anything. Or they are exactly 8 apart, which means that I've got 2 values on disk that I'm trying to determine the proper order. And if you're familiar with disk access, you know that you have to seek to a particular location and then read in the values. If these were true disk operations, this implementation would be torturously slow. But because of mmap, the ability to memory map files, the operating system handles the paging in and paging out of data in such an efficient way that you actually don't notice that you're loading up information from disk. This is really truly where the performance benefits come. All I've done is taken the structure of mergesort and recast it into this context where if you want to retrieve the value at a certain location, you have to seek to it and then read in the int stored there. And so this here gets the left and the right, and it says, are they out of order? Okay, write them back out in the proper order, right, left. The recursive steps are right here. Find the midpoint, do that recursive call on the left-hand side of the array and the right-hand side of the array. Now in this case, it's not a real array. These are result and A are memory mapped files right to the disk, and the operating system is handling all the paging in and paging out of the data. The final process, as we've identified, is a merge that somehow has to go through and identify the 4 cases. Is the left part of the file or the right-hand part of the file? Am I inserting the smaller one? Have I exhausted the one on the right-hand side? You see the structure here is pretty much the exact same as what you saw with the mergesort. And the fun part is now I can run this and demonstrate that I can sort an external file without resorting to what would otherwise be a security situation where you just arbitrarily execute through the system call, a utility on the operating system. Here I've got a small set of data that is in random order, as you see. I'm going to sort it using mergesort. In this case, it's called mergesort file. And now when I output the information stored on disk in that file, it's in sorted order. This is actually a really impressive contribution where the code doesn't look any more complex because you understand the nature of the mergesort algorithm. All the complexities are just, well, how do you access data from a memory map file and how do you write and read integers from that? Once you understand that, The implementation speaks itself. So this particular instance to complete the module on mergesort shows how you can take that same algorithmic approach, divide and conquer, apply it to a larger problem that can be broken up into 2 subproblems, each one of which is recursively solved. And then you have a final step that does the merge and produces a final solution from the 2 partial spots. In terms of the performance, it gives me the n log n behavior that I was so desiring of. As I mentioned earlier, that's the sweet spot with many different algorithms. I could very easily come up with a naive algorithm for sorting that's order n squared, but that would lead to problems that are 100 times bigger or 100 times more complicated to solve when in fact the problem size has only gotten 10 times as big. We're always striving to work on problems of ever increasingly larger size, which is why we always have to look for n log n algorithms just as you've seen here. And that completes this extension to mergesort.